All right, guys, we're going to start off here with just a parent function chart. So this is just a table of kind of our basic functions, and then we're going to work on transforming them from there. So the first function we're going to look at is called the constant function, and that's going to be f of x equals, I'm going to put c here. So c could be any number. It could be 5, it could be 2, it could be -3. And kind of the key on this one that is that no matter what x is, and I'm just going to throw some kind of random numbers in there from -2 to 2, y is going to be constantly c. And so our graph on that one's always going to be a horizontal line at wherever c is. And so if that was like, f of x equals 2, that would be a horizontal line at 2. It could also be like f of x equals -3, and then it would be a horizontal line at -3, just wherever that is. And so I'm going to put a little description down here, and so I'm going to call this a horizontal line. And so for domain on range on this, for the domain, I'm going to say that that's -infinity to infinity, because it goes left and right forever. But for the range, if you just look at the graph, I would actually say that's just c, because it never moves from that spot. All right, next here we're going to focus on linear, and so for linear, our parent function is going to be f of x equals x. And so if you make our little table here with those same x values, you'll see that x and y are always the same thing. That's the big idea on that function. And so that creates a line that looks like this. And if you want to think of it as a slope of 1 and a y-intercept of 0, that is a good way to think about it. I always describe this one as a sloped line, as opposed, I don't like calling it a straight line, I like calling it a slope line, especially because the idea of slope is so important on the linear equation. Our domain for this one is -infinity to infinity again. We can plug in whatever we want. And then the range is actually also -infinity to infinity. So that's that. All right, next up we got quadratic. So our parent function for this is going to be y equals x squared. And so I'm going to use those same x values again here. But now you can see that this turns into 4, +1, 0, 1, and +4. And so that makes kind of a shape like this. And we call that a parabola is the shape. And if you want to say that it's U-shaped, I can kind of agree with that. And so for the domain on that, it's going to be -infinity to infinity. Again, you can see it goes left and right forever. And then the range on that is actually not -infinity to infinity, because you can see it starts at 0 and then goes up from there. All right, next up we got the square root function, which is going to be f of x equals the square root of x. And so for this one, I'm actually going to pick my x values a little strategically here. I'm going to do -1, 0, 1, and then 4, and then 9. And I kind of pick these since I know I'm doing square root. That's going to come out to 3, 2, 1, 0. And then this one's going to actually be imaginary, which we're not going to graph. So I'm going to graph my points here, and we'll go ahead and just draw a quick sketch of that line. How I describe this one is a half of a parabola on its side. So you can kind of see that if we did have kind of the other half of this parabola going this way, you could see that full parabola that's on its side. This one's just half of the parabola. That's really because of it's got to pass the vertical line test, or else it's not a function. Now our domain on this one is actually going to be from bracket 0 to infinity. And we kind of learned that domain rule in the last section, whereas the inside of a radical must be greater than or equal to 0. You can also see it on the graph, that the graph only exists to the right of 0. And for our range, you can actually see that the lowest point is here 0 as well, and then it goes up forever. So range is the lowest point to the highest point. So that's how I got that. All right, next up here, we're going to start off with the absolute value function. So this one's going to be f of x equals the absolute value of x. And so for this one, I'll go ahead and go back to that -2 to 2 points here. And the absolute value is just going to turn all of those positive. And so this actually makes a V-shaped, going like that, that's how I would describe it, V-shaped. Now our domain on this one is going to be from -infinity to infinity. And our range is going to be, you can see the lowest point is 0, so it's going to go 0 to infinity. All right, next up here we have our cubic function. So for this one, it's going to be f of x equals x cubed. I'll go -2 to 2 again on my x's, and then I'll cube them for my y's. You'll notice that cubing them does not turn them positive, keeps them whatever they were before. So this one is going to look like this. And I never had a great description for this. The best description I've ever heard is an unfolded paper clip. If you kind of think about unfolding a paper clip, it might look like that. If you have a better description for me, I'd love to hear it, so you can tell me about it then. For the domain on this one, it's going to be -infinity to infinity. It goes left and right forever, and then it also, in this case, goes up and down forever, so that range will be the same as well. All right, next up here, we got our rational equation, and this one, the parent function is going to be 1 over x. And if I do these ones here, this would be -1/2, -1. This is actually undefined. 1 divided by 0 is undefined, and this will be 1, and this will be 1/2. All right, so this one, it kind of looks like this. All right. And so in our domain, it's actually including every number except 0. So it's going to be -infinity to 0, and then from 0 to infinity. And the range actually also includes, excludes 0 on this one. All right, exponential and logarithmic, we're actually going to touch on those more later on, so you can go ahead and skip those for now. All right, now on to the next section here. So we got our essential questions. How do graphs represent functions? And then how do you use a graph to evaluate a function? So first off, a parent function we talked about on the previous page is the unstretched, unshifted, and unreflected. I'll put that one out here. Form of a function. Okay, so unstretched, unshifted, and unreflected. Domain is the list of all possible x values, usually listed in interval notation for us. And then this is the list of all possible y values, and that'll also be in interval notation. All right, next up, the vertical line test tests whether or not a graph is a function. If any vertical line hits the graph more than once, it is not a function. It means that for any one x, there cannot be more than one y. Okay, so this one asks if these are a function. So to test if it's a function, I just draw a bunch of vertical lines. If any of those hit the graph more than once, then it is not. And so I can see right away this one, that vertical line hits that graph twice, so that's a no. This first one, though, I would say is a yes. And then next up for domain and range. For domain, I just kind of look at the furthest left and the furthest right point. And so the furthest left point, I would say, is a -4. And the furthest right point is a +3. I would use brackets there. I know there wasn't closed dots on the picture, but I would assume if it's the line, it is a closed dot unless they specifically put an open dot. All right, then next up for range, it's kind of the lowest point to the highest point. So I see this is the lowest point, but that's actually the highest point in the middle there. So I'm going to say that's from -1 at that lowest y value to 3, that highest y value. All right, next up here, we're going to use the graph to evaluate the function. And so what this is asking is, what is the y value at the specified x value? So when they say this one, f of -3, they're saying x is -3, and if x is -3, what's y? So I would go back 1, 2, 3 and find the graph. Now you can see it's right there at 0, so the y value is 0. Now this one they say x is 0, and if x is 0, the y value is way up here at the y value of 3, so our answer is 3. For f of -4, they're saying x is -4, and then they're saying x is 2. Do those two separately, and then add the results. So if x is -4, I'm back down here, and so that's the y value of -1. And I think that if you're saying that's -0.9, I think I meant that to be -1, but if you said it was -0.9, I wouldn't argue with you. And then when x is 2, I'm right here at the y value of 0.5. And so I would say this answer is negative 0.5. All right, the last question here, for what x values does f of x equals 2? Now you can see they didn't put the 2 in there, so this is actually saying that y equals 2, and if y equals 2, what does x equal? So I would draw like a horizontal line at y equals 2, and I actually see that there's 2 spots where that happens. So I'd say x could equal negative 1, or x could equal 1. That'll never happen the other way because of the vertical line test, but the horizontal line test does not really apply, and so it is possible for me to have 2 answers here. All right, you can skip this other graph. We'll go ahead and do that in class as a warm-up. All right, next up we'll graph some piecewise functions here. And so how I always graph these, and there are other techniques for this, but I always use a t-table to start, so I would go ahead and do that. We'll do x and y. And the numbers I put on my t-table, I always go to what I call the border number, which is kind of the x value where it switches from one to the other. And that number, I'm going to write it twice. I'm going to write it once down there, and I'm going to write it once up there. I'm going to go ahead and color code this. And so up here, I'm going to put some numbers that are smaller than negative 1, like negative 2 and negative 3. And all of these numbers I'm going to be plugging in here. Now, under here, I'm going to put some numbers that are bigger than negative 1, like 0 and 1. And all of those numbers I'm going to plug into here. So now when I'm plugging them in, I'm just plugging them in for x over on this function right here. So it's going to be 2 times negative 3 plus 3. And if you can do this in your head, I think that's fine. So then 2 times negative 2 plus 3 would be negative 1. And then 2 times negative 1 plus 3, this would be 1. Now, some of you may be thinking that I should not have plugged in negative 1 into this piece because there's no or equals to here. That's actually correct. We are going to, actually, let's deal with that now. So how we deal with that is that when we graph this one, we're going to graph this one as an open dot. These ones are going to be graphed as closed dots because I actually plugged them into the correct piece. But the open dot, I kind of plugged into the fake piece. I need to do it anyway. I still need to kind of plug it into the wrong piece there, but I'm just going to show that I shouldn't have plugged it in by doing an open dot instead of a closed dot. All right, so now my green piece is going to be 3 minus negative 1, and so that turns into 4. And then 3 minus 0, it's going to be 3, and then 3 minus 2 is going to be 1. Now, all 3 of these were plugged into the correct piece, so these are going to all be closed dots. So on these ones, there's only going to be possible for there to be open dots kind of at the border there. So non-border numbers will always be a closed dot. Okay, so then next up, I'll go ahead and graph these points. And so my blue graph will have a negative 1, 1. Oops, that's an open dot. Okay, and then negative 2, negative 1, and then negative 3, negative 3. Now this one goes left forever, and you can kind of visualize that by our rule. It says we only graph that one if x is less than negative 1. So that means to the left of negative 1. So then my green graph is kind of going the other direction here. And so I'm going to graph this one at negative 1, 4. That's a closed dot. Oh, that was only 3. All right, let's go up to 4. And then 0, 3, and then this one's going to go right forever since that one only exists when x is greater than or equal to negative 1. And so you can really see the conceptual idea of the piecewise function here, which says it's supposed to be this positive 2 slope to the left of negative 1. So you can see this blue line has a positive 2 slope if you read it left to right, but it stops once we get to negative 1. Then we're going to do this one with a negative 1 slope once we get to the right side of that. So you really see that function cut into 2 pieces. Now, next up, we're going to evaluate this function, and the great thing about this is that these function evaluations, we can actually do it in this up here, we can do it on our graph over here, or we can do it in the table over here. They're all really representing the same thing. I'm kind of a graphical person, so I like to use the graph. Some people like the table, some people like the equation, doesn't matter. So on my graph, I see that when x is negative 3, like we did on the previous page, my y value is down here, also at negative 3, so that one's negative 3. Now for x equals negative 1, you may be thinking, do I go to the open dot or the closed dot? In these cases, remember the open dot is not really there. That's just saying that's where it would be if it was there. So we'll always use the closed dot in these situations. So at negative 1, I'm going to say my y value is 4. And then lastly, f of 2. So I go over to 2. I can see my graph is right there at a positive 1 y value. My domain here, I would say, is negative infinity to infinity. I see it goes all the way from starting left forever, right forever. You may think that there's a gap here at -1, but I would actually argue that there's not, because as soon as this one stops, this one starts back up, so we have no missing x values. For my range, I see that this goes down forever, and then and this one goes down forever also, in fact, and then the highest point it ever gets to is right there at 4. So I'm going to say from negative infinity to 4. All right, next up here, we'll go ahead and do this other graph. So we will go ahead and make our table again. I see my border number this time is 0, so that's the number I want to do twice. I'll do it and color code it here. So I'll do the border number twice. And once again, that's based on where this switches from one to the other. And then I'll put some numbers that are greater than 0, and we'll also put some numbers that are less than 0. Oops, my green here. All right, and so these ones are all going to go into, and I actually kind of tried to trick you here. You can see that those need to go in that one because they're actually less than 0. So I did switch around the order. That does happen sometimes. So these ones are going to go up here as they are greater than 0. Now, the less than 0 ones, there's actually no x to plug in here, so that's actually easier. It's just all -3, no math required. And then the other ones I do need to plug in, so I got 0 squared minus 3, which is -3, 1 squared minus 3, which is -2, 2 squared minus 3, which is +1. Okay, so let's go. Oh, and one more thing is that this one was missing the line underneath, so that's the one I kind of cheated and plugged in the wrong spot, so this should be an open dot. These ones should be closed, though, because those actually were plugged in. This one, though, is all closed dots. So my green one here, 0, -3, and then like that. So like we saw in our parent function chart, that's going to be a horizontal line going left forever. Now, the interesting thing here is you can see that our open dot and closed dot are in the same spot. Whenever this happens, the closed dot wins. And so I just kind of think of it like that open dot gets filled in by a closed dot. It takes over. And then we have a dot here, and then 2, 1. And you can see what this one is in our pieces. We have the left piece is a horizontal line at -3. Our right piece is a parabola, and so you can see that as well. Now to evaluate the function, once again, I like to use the graph here, but you can use this or the table if you want. At -3, our y value is right there, also at -3. At 0, our y value is still at -3, and I am able to use that point since it's really a closed dot. And then at 2, it's at 1. Our domain here is negative infinity to infinity, no break in our x values. Our range, I don't see any points lower than -3, so I'm going to start it there, but I see it goes up to forever to infinity. Last one here we'll do as a warm-up in class, so you can skip that one.